Hello everyone, welcome back to MP Coding. This is the second video in our FreeRTOS synchronization primitives series. In the previous video, we talked about binary semaphores. We covered what a binary semaphore is with examples and the timing diagrams, and explored priority inversion. Finally, saw how to use an ISR to release a semaphore. If you're new to this series, I highly recommend watching my previous video on binary semaphores before continuing. In today's video, we're going to discuss the counting semaphore along with some practical examples. A counting semaphore is similar to a binary semaphore, but its value can be greater than 1. It's useful for counting events or managing access to a pool of identical resources. For example, you can use a counting semaphore to control access to a pool of 5 buffers. Let's look at a practical visual example. Here, we have 2 parking spaces and 3 cars that want to park. First, car 1 parks in space P1. Then car 2 takes P2. Now both parking spaces are full, so car 3 has to wait until one of them becomes free. When car 1 leaves, car 3 takes the now available P1 space. Later, car 2 also leaves, freeing up P2, and car 1, which was waiting, can park there again. In this example, the parking spaces act like a counting semaphore with a value of 2. And the cars represent the tasks that need access to the shared resource. So, just like in a counting semaphore, only 2 tasks can hold the semaphore at the same time. And any additional task must wait until one of them releases it. Let's start with an example using the STM32. As in the previous video, I will be using the STM32F429i Discovery board, but you can use any STM32 board you like. Here, give it a name, and click Finish to continue. I won't initialize the board with the default mode, so I'll click No. Next I clear out the default pinout so we can configure everything from scratch. First, I'll set up the RCC and select the high-speed clock source to the external crystal resonator. In the clock configuration tab I set the HSE input to 8 MHz and configure the system clock to run at 180 MHz. Now I'll open the middleware section and enable FreeRTOS, selecting the CM-Sys v1 interface. In the FreeRTOS settings I'll enable counting semaphores so we can use them in the examples. Okay, if we look at the tasks and queue, we can see the default task already defined. And in the timers and semaphores, we can see the counting semaphore table. Here, we can add a new counting semaphore, like we did in the previous example of a binary semaphore. But in this example, I will not going to use the CM-Sys API. I plan to use the native FreeRTOS API in this demo. I won't define semaphores or tasks inside CubeMX, I'll create them in code instead. That's all for FreeRTOS setup. For connectivity I'll enable USART1 for the virtual COM port so we can print messages to the serial console. Then these GPIO pins I will set as output pins. As you know from the previous example, I have connected these to the logic analyzer. Finally, this PA0 is set as an external interrupt pin. In this board push button is connected to the PA0 letter in the ISR example. And in the NVIC I'll enable EXTI0 and set its priority to 7. Which places it below the kernel interrupt priority level so it can safely interact with the scheduler. Finally, under System I'll change the HAL time base source to a hardware timer, not system tick, because the RTOS uses system tick. That's all for CubeMX setup. Generate the code. Okay, in the generated code, you'll see that the cm-sys-os.h file is included, but we won't be using the cm-sys API in this example. So, I'll open cm-sys file and copy all the necessary include headers. And then remove the cm-sys-os.h line from our main file. And paste those copied includes. Since this example only uses semaphores, we don't need these other headers. I will remove those. We'll just keep FreeRTOS.h, task.h, and semaphore.h, that's all we need for this demo. When I scroll down I can see the pre-generated task handle and the task function stubs that CubeMX created. Because I'm switching to the native FreeRTOS API, I'll remove the cm-sys includes and the cm-sys task creation lines. Here in main function. Also remove all of these lines. In the bottom, remove this function definitions also. Those were auto-generated by CubeMX. Now let's start implementing the same functionality using the native FreeRTOS APIs. First, let's create a semaphore handle. And I'll name it Counting Semaphore Handle. In this example, I'll use 3 tasks to demonstrate the concept, so let's go ahead and create 3 task handles here. Now, let's create the task functions that each task will run. Here in the main function, let's create the counting semaphore using xSemaphore create counting function. We need pass 2 arguments, the maximum count and the initial count. In this case, the maximum count will be 2, and the initial count will be 0. We'll store the return value in our counting semaphore handle. Next, I'll check if the counting semaphore handle is null or not. And result will print using UART. And then, let's create the tasks using xTaskCreate. For this function, we need to pass these parameters. The task function. A name for the task. The stack size. Parameters. The priority level. And finally, the task handle reference. So for task 1, I'll pass the task function, give any name for it, use a stack size of 200 words, set parameters to null, set the priority to 3, and finally pass the task handle reference. Next, let's create the other 2 tasks, task 2 and task 3. Change their names, handles, and priorities. For task 2, set the priority to 2, and for task 3, set the priority to 1. So now, task 1 will be the highest priority, task 2 will be medium, and task 3 will be the lowest priority. Finally, let's start the scheduler using vTaskStartScheduler. This will begin executing all the created tasks according to their priorities. After starting the scheduler, the program control is completely handed over to the FreeRTOS kernel. So, the super loop will never be reached, unless the scheduler fails to start due to an error such as insufficient heap memory. Okay, now let's edit the task functions to implement the counting semaphore behavior. In task 1, before entering the main loop, I'll give the counting semaphore twice to initialize its count. Next, inside the loop, let's take the semaphore using xSemaphore take. We'll pass the semaphore handle and set the block time to port max delay, so the task will wait indefinitely if the semaphore is not available. Next, to indicate that task 1 has taken the semaphore, I'll toggle the PG13 GPIO pin. Next, let's add a 400 millisecond delay using vTaskDelay. The PDMS to ticks macro converts milliseconds into ticks. After the delay, let's give the semaphore back, so the task itself releases it for other tasks to use. To indicate that the semaphore has been released, let's toggle PG13 again, so we can visually track when the task takes and releases the semaphore. After releasing the semaphore, let's add another 500 millisecond delay, so giving other waiting tasks a chance to take the semaphore and run. The other 2 tasks will follow the same pattern, but with different timing settings. So I'll just copy this structure and adjust the delays for task 2 and task 3. And I'll change the GPIO pins for the other tasks so we can visually distinguish each task's semaphore activity. What I've done here is, in task 2, I set the waiting time to 500 milliseconds, and in task 3, I set it to 600 milliseconds. Okay, all the setup is complete. Let's run the code and observe the output. Here on the logic analyzer, you can see that all the GPIO pins are toggling, indicating that the tasks are taking and releasing the semaphore correctly. In the serial monitor, we can see the message semaphore created. The extra characters like T1 are unwanted memory artifacts. If you check the UART, the message length should be 19, not 23, which is why these extra characters are printed. Okay, now let's analyze the counting semaphore behavior using the logic analyzer. At the start, the semaphore value is 2. Task 1, the highest priority task, takes the semaphore, decreasing the value to 1, and sets PG13 high. Task 2, the medium priority task, takes the semaphore next, decreasing it to 0, and sets PG14 high. Task 3, the lowest priority task, tries to take the semaphore but must wait, since the value is 0. At around 0.4 seconds, Task 1 releases the semaphore, increasing the value to 1, which allows Task 3 to take it and set PG11 high. At 0.5 seconds, Task 2 releases the semaphore, bringing the value back to 1, but no tasks are waiting at that moment, so it remains 1. At 0.9 seconds, Task 1 completes its cycle and takes the semaphore again, setting PG13 high. At 1 second, Task 3 releases the semaphore, setting PG11 low, and then Task 2 takes it again, setting PG14 high. This pattern continues, demonstrating how a counting semaphore allows multiple tasks to access limited resources while blocking tasks when the semaphore value reaches 0. The logic analyzer timeline clearly shows which task holds the semaphore and when other tasks must wait, illustrating the blocking and synchronization behavior in real time. Exactly, this behavior is just like the parking example we discussed earlier. The counting semaphore acts like the parking spaces, and the tasks are like the cars. Only as many tasks as the semaphore value can park at the same time, and any additional tasks must wait until a space becomes available. You can check the README file on GitHub for more details about this example and the full source code. Okay, next let's check how the ISR behaves and how it interacts with the counting semaphore. Here, Task 1 isn't taking any semaphore, it runs freely and toggles GPIO PG11 every 500 milliseconds. Task 2 and Task 3 take the semaphore, toggle their respective pins, and wait for 1000 milliseconds, but they never release the semaphore. When the external GPIO interrupt occurs, I'm releasing the semaphore only once. This ISR releasing pattern is something I discussed in the previous video. It ensures that tasks are unblocked safely without causing unexpected behavior or priority inversion. Okay, that's it for the code. I've run the program, pressed the button multiple times, and captured the output on the logic analyzer. Now, let's analyze what's happening. PG11 toggles periodically. This Task 1 isn't related to the semaphore. Here, I've added some case numbers to make the behavior easier to follow. Case 1, initialization. At startup, Task 2 and Task 3 each take one of the two available semaphore tokens. They hold the semaphore, never release it, and then block. The system waits for a button press. Cases 2, 3, 4, each button press releases one semaphore from the ISR. The scheduler wakes the highest priority waiting task, which is Task 2. PG13 goes high while Task 2 runs for 1 second, then low when it finishes. Cases 5 and 6, a button press releases one semaphore, and Task 1 acquires it and runs. Before Task 2 finishes, another button press releases a second semaphore. This time, Task 3, the lowest priority task, acquires it. The result is that Task 2, PG13, and Task 3, PG14, run concurrently. When both tasks finish, they return to the waiting state again. That's it for today's tutorial on counting semaphores. We explored how they work, how multiple tasks can share limited resources, and how an ISR can release the semaphore to unblock waiting tasks. In the next videos, we'll dive into mutexes and other synchronization primitives, and see how they differ from semaphores. If you found this video helpful, make sure to like, subscribe, and hit the notification bell so you don't miss the next lesson. Stay tuned.